So, in this session we are going to discuss about the phenomena of boiling. Majorly it will be qualitative discussion, because you see that boiling, the most common type of boiling is heterogeneous boiling, where we have a hot solid surface. And the problem of quantification is that these surfaces are highly irregular from its microscopic point of view, right. Like they have got these fissures, pits, pit holes, scratches, etc., which are potential nucleation sites for vapor bubbles during the course of boiling. So, and this type of phenomena is definitely it is quite difficult to quantify. So, we will be majorly discussing the qualitative features of boiling in terms of boiling curve as per the experiments of, first it was performed by Nokiyama in 1934, right. Yeah, it is 1934, and later by Farber and Skora, which is a kind of extended versions of Nokiyama's experiment in 1948. So, we will be discussing that, but the only quantitative scope we have in case of homogeneous boiling, which is more theoretical perspective, right, because homogeneous boiling we rarely encounter or implement in process industry or in real life. So, if it is a homogeneous boiling, definitely there are some scope of quantitative analysis, but majorly we have to stick to qualitative discussion. So, qualitatively you see that what is the most easy and the standard way of conducting boiling experiment. And generally there are two different types of boiling. One is typically conducted in batch mode, that is called pool boiling, and another one is the flow boiling, which is practiced in industry. But to characterize the boiling, we have to focus on its batch mode, that is a pool boiling test. Okay. So, one is pool boiling, that is batch mode. Another one is flow boiling, where the liquid may be flowing continuously through a boiler tube, and there will be different regions from this entry to the outlet of the tubes, where at the outlet, at the entry it is a subcooled liquid, whereas at the outlet the entire liquid is being converted into some superheated vapor, right. So, that is the regime of flow boiling. So, this is continuous mode. So, in pool boiling, the experiment the experimental setup, which is due to Nokiyama, he performed this experiment with this pool boiling setup, and another one is Farber and Skora in 1948. So, what is the experimental setup? They have used an insulated container right, where we have an electrical coil as the hot surface or a weir, and this is the liquid, right. So, we have these vapor bubbles being generated, and here in the liquid, if we dip a thermocouple, we can record the temperature, right. Now, you see that in the coil, I must know the surface temperature of the coil. So, here from voltage and current reading, we can calculate heat flow rate or heat flux rather, which is V into I divided by 2 pi capital R into L. So, that is the surface area and wherefrom we are getting the heat flux. And additionally, Ts, which is the surface temperature of the solid, can also be calculated upon solving the equation of conduction. Right, because far away the liquid temperature is known and this much heat is being dissipated. So, we can solve this conduction equation, right, and from there we can calculate the surface temperature. So, once we have calculated the surface temperature, we define excess temperature TE as surface temperature minus saturation temperature, right. That is the boiling point, saturation temperature at that specific pressure. So, the boiling curve is a plot of heat flux, or more importantly heat transfer coefficient. And how we can solve? Q is equal to boiling heat transfer coefficient Ts minus T infinity. So, you see that Q has been calculated, we know Ts, T infinity is the saturation temperature. So, basically this is nothing but excess temperature. So, from there we can calculate this Hb, which is basically the heat transfer coefficient for boiling. So, plot of this heat flux or heat transfer coefficient with respect to Te in a double logarithmic plot, a double logarithmic space. So, you see, now we will try to discuss this plot, the nature of the plots and the different regimes with details and what are the corresponding physical phenomena, what is happening, right. So, if I look into this double logarithmic plot, log of Hb versus log of Te, I will get some sort of curve like this. Right. So, here where we start A to B, then C, D, these are the different regimes E, F and G. So, this is regime 1, regime 2, 3, 4, 5, 3, 4, 5 and 6. Okay. So, this Hb grows to a maxima, right, and generally it will decay down to a minima and again started increasing for a very high excess temperature. So, we have to understand the meaning and the physical situation in different regimes separately. So, you see when we apply a very small, so let us discuss regime 1. A to B. Here excess temperature is around 0 to 4 degree Fahrenheit, very small excess temperature. And what is the situation? If this is the weir, we have very small bubbles, right, from different spots, they moves up like this. Okay. So it is very small bubbles being generated from different locations. Most of the bubbles, most of these tiny bubbles collapse before reaching the free surface. Right. So majorly they will be generated and most of the bubbles will collapse before reaching the free surface, and this regime is called interfacial evaporative regime. So this is called interfacial evaporative regime. So next, from B to D, the major regime is B to D, that's called the nucleate boiling regime. So B to D, regime 2 and 3, nucleate boiling regime. And here in these two, what happens, we will separate it, this is being further divided into two regimes, 2 and 3. So primary or initial nucleate boiling regime, that is 2. Here what is the situation? See, here moderate sized vapor bubbles are being released from some spots like this. Okay? So here if I try to, and here the regime 2, it's 4 to 11 degree Fahrenheit, right. So isolated bubbles are formed at the surface of the weir, but most of them collapse before reaching the free surface of the liquid. Because bubble formations at reasonable rate starts at B, the point indicates the onset of nucleate boiling. So again the features are more or less same, but here the bubble density more or less same as interfacial evaporative regime, but here the size is very small, here the size increases, right. Moderate, small to moderate size. So small to moderate sized vapor bubbles are generated. Most of the bubbles collapse before reaching the free surface of the liquid, right. And point B is marked as onset point or onset of nucleate boiling, right. Next is the second nucleate boiling regime, So, that is regime 3, and here the temperature is 11 to 65 degree Fahrenheit, right. So, excess temperature increases, and here the bubble generation is much more vigorous. So, over the entire surface nearly of this solid, the bubbles are being generated, right. They move up in the form of columns like this. So, what are the characteristic or salient features? So, you see a large number of vapor bubbles are generated and vigorously rise to the liquid and escapes from the free surface. So, here bubble density increases, most of them reaches the free surface, induces, their movement and generation and movement through the liquid induces motion in the liquid itself. And the breakup and coalescence, they form, the vapor bubbles rise as jets or columns and then form bigger bubble slugs. Vapor forms jets or columns of liquids or columns of vapor, columns giving rise to vapor slugs, right. And finally, here the breakups and coalescence is very prominent here. The breakage and coalescence of vapor bubbles are also quite frequent, right. So, that is the second nucleate boiling regime. And this point where the flux reaches the maximum, it is called the critical point where Q is equal to Q max, and that is QC, the critical point flux, which is the maximum flux, and there are certain empirical equations, we are not going to discuss it. This critical flux can be expressed in terms of T and other liquid properties. There are a lot of equations, right, based on these empirical studies, but the equations, the form itself is quite complicated. So, that is why we are not going into the detail, and it is not recommended for that we have to mug it up, right, we do not require the expressions. So, when the excess temperature exceeds the characteristic value at D, that is nearly 65 degree, what will happen? Here it drops, and why it drops? Because the vapor, the number density of the vapor at the surface of this bubble is so high that they often coalesce on the surface itself, producing a transient film, but the film is not stable, right. So, that is why this region is called, from here to here it is entirely the film boiling, right. From C to D, this region is called this transition film boiling, okay. So, or unstable or transition this film boiling. So, I am erasing this part, okay. Point D, next to that film boiling begins. So, regime 4 which is from D to E. This region is called or referred as unstable or transition film boiling. Right. So, you see that in this region, what are the characteristics? The mode of boiling changes from nucleate to film, and here the bubbles are formed in so large number that coalesce right on the heating surface, as I mentioned, to form a film of vapor. So, unstable film is formed on the surface because of local coalescence of vapor bubbles. However, that film is actually unstable. It may appear in the at one moment and it may disappear in the next moment. So, the formation of the vapor film on the surface is not complete in this region and the film is discontinuous. The film may even disappear momentarily and then reappear. This regime represents partial nucleate boiling or transition boiling, right. So, next, that is from E to F. So, here what is the picture? The picture is very similar to the previous because the film cannot be seen as such. So, dense bubbles being generated. Right. So, there is some part which is occupied by film. So, in the next regime that is from, so in the transition film boiling, the temperature may varies from 65 to 400 degree Fahrenheit. So, it is 65 to 400 degree Fahrenheit. Okay. So, next is regime 5, E to F. Temperature is 400 to 1000 degree Fahrenheit. So, here the situation is that here we have a stable film on the surface, right, and the vapor bubble generates from the upper surface of this film. So, that is the situation here. So, what are the basic characteristics? So, continuous vapor film always blankets the heating surface. Continuous vapor film that blankets the heating surface, which is stable at the same time. The surface heat flux decreases significantly, although the excess temperature may be as high as few hundred degrees. After the point F, definitely this is the next regime. Here you see that the surface of the film, this acts as a secondary nucleation plot for the bubbles. Okay. So, this is the continuous film boiling and it passes through a minima here. So, from F to G, next it is regime 6, F to G. Here the temperature is greater than 1000 degree Fahrenheit and it may continue to any extent, depends on how much excess temperature or how much the surface temperature we can actually impart in this heating coil, right. Because if it may happen that heating coil may burn out, right, and that is commonly known as the problem of boiling crisis. So, here in this region, the secondary nucleation spots are very prominent. The film definitely it is stable, but there are convex regions from which we have this bubble generation. And here in this region, radiative heat transfer becomes important. Okay. So, over this region radiative heat transfer is important. Like, what are the features? The where temperature increases so much, the radiative heat transfer becomes important. The characteristic of this regime F to G, that is the regime 6, these are the fundamental characteristics, and if the excess temperature is too high, the heating ware may even melt. The melting or burnout of heat transfer surface is sometimes called boiling crisis. May encounter boiling crisis. Okay. So, most important feature of this regime is that we have radiative heat flux becomes important, and this curve actually we have to terminate because we can't go beyond, as there may be melting or burnout of this heating coil. So, that's about the boiling curve. Now, you see that on the onset of for the shift from nucleate to film boiling, we have a phenomena what we observe in kitchen, that's called Leiden frost phenomena, right. If I have a hot surface and a liquid drop falls on the surface, what will happen? Immediately you see, say the liquid drop is in large size, we are enlarging it. There will be generations of vapor, right. It will sit, the drop will sit on the surface, and there will be nucleations immediately, and there will be switch from nucleation to film. So, there will be a film, and film has got a high pressure. So, it will eject the drop again from the surface. So, it will move up like this, and again its size decreases, the same phenomena is being repeated, right. So, it will go on doing this before it finally evaporates. So, this is called the Leiden frost phenomena. So, when water droplet lands on a hot surface, a film of steam immediately forms between the droplet and hot water, and because of the thickness of the vapor film increases very quickly by further evaporation of the liquid, the droplet experiences an upward thrust and it again falls back because the film is getting released. So, this is called the Leiden frost phenomena. Leiden frost phenomena is caused by film boiling and occurs for evaporating droplets in hot surface corresponding to the regime, this regime, that is a stable film boiling here, right, this regime 5. Now, next it was this phenomena what we are going to discuss now. It is typical in many physical science, and that is hysteresis. Here also we observe it. It was first actually observed by Nokiyama, that you see that if HB versus TE in log we plot, the actual curve should be like this. But what was observed, that from this critical flux point, there is no further increase of HB, it directly jumps to here, right. So, with the increase of T, here the observation is instead of decreasing, it remains flat. So, actually the film boiling is being initiated, but it is remaining flat. The exact reason of boiling hysteresis, there are different opinions, we are not going into the detail. And similarly, if we start from somewhere here and go on reducing the temperature, instead of following this curve, it will follow a line like this. So, the pathway for increasing T and reducing T, these two are different, and this was first reported, and there are a lot of justifications, different justifications from the thermal science, they are available, but there is no direct strong reason by which we can exactly justify this boiling hysteresis, and it's complex also. So, we are not going into the detail of this boiling hysteresis. Now, mechanism regarding this, that's all basically the qualitatively we have discussed about boiling. Now, regarding the mechanism of nucleation, you see that what happens generally, there are two different types of boiling or respective bubble nucleation. One is homogeneous, another is heterogeneous. Okay. So, homogeneous boiling, as I mentioned, it is rarely encountered in industrial situation. Mostly we have the heating surface, and there we have this typical heterogeneous boiling. So, nucleation of bubbles. So, this may be homogeneous and heterogeneous. So, homogeneous means from the superheated liquid, which is itself a metastable or unstable state, right. So, when we have a liquid which temperature is above and over the saturation temperature, naturally there will be, from the bulk of the liquid, we will have the generation of vapor bubbles. Like in an indefinite bulk of liquid over certain region, if I focus certain these high energy laser beams, it can happen that over this specific region the liquid becomes superheated and there will be homogeneous bubble nucleation. So, this is typically the homogeneous boiling, right. And on the other hand, the heterogeneous boiling at solid surface, we have different nucleation spots, right. Like you see that microscopically we have a pit hole, like here we have a pit hole in this solid. Its dimension is in the order of micron. Now, you think of a water, this droplet, entirely it is filled up with water, right. So, here the water droplet, we have a water droplet here. Now, what will happen? We have in physical chemistry Kelvin equation, I am not going into the detail. See what it states, that if for a flat surface at a given temperature, flat surface means between liquid and the vapor, if the saturation pressure is Psat 1, right, then when we just curve that surface, for a curved surface, vapor and liquid, and here at the same temperature, if it is saturation pressure is Psat 2, right. For this the saturation pressure actually it's higher. So, P2 sat is higher than P1 sat. So, it is expected that this will boil, this will vaporize at lower temperature, right, because it is having higher vapor pressure at the same temperature. So, and the condition of boiling is that the vapor pressure is equal to the superincumbent space pressure, that is the pressure above and over this liquid surface. Here what is the pressure? If it is equal to the vapor pressure, that is the condition of boiling. So, if the vapor pressure for a curved surface increases, now what is the obvious consequence? The consequence is that this will reach the superincumbent space pressure at a much lower temperature. So, here for this type of this curved surfaces, curved liquid vapor interface, the boiling is much more favored compared to this. And with the reduction of this Kelvin equation states that this ln of P2 sat by P1 sat is proportional to the curvature, that is 1 by this radius of curvature. Now, as you go on, see, as you go on reducing this droplet size, if it's a very small crack or fissure, so locally the liquid will have a very small r. So 1 by r is high. As a consequence, P2 sat will be much higher than the flat liquid surface vapor pressure, and inevitably what we can note that maybe at a much lower temperature than that of normal boiling point, this we will have the generation of these vapor bubbles, right. And that we sometimes observe in kitchen, that when we heat the liquid, right, at some much lower temperature we have certain spots where from we get this continuous small bubbles is being produced, and that's because of Kelvin equation and because of this local curvature which facilitates the local evaporation or local boiling, right. So, this is the reason that why this heterogeneous nucleation is not only technically favored, but it has got also certain advantage, because we can achieve the same amount of vapor in heterogeneous surface than homogeneous surface, even if we think of a hypothetical situation where both are implementable with the same economy, right. So, for homogeneous nucleation, we have a quantitative aspect. Quantitative analysis we are going to do. So, here you see a vapor bubble, it nucleates, right, in a pool of liquid. So, here its pressure is PV, liquid pressure is PL. The temperature of the liquid is TL, and they are in thermal equilibrium. Right, because this TL is greater than T sat, as the liquid is superheated, right. So, here because of the thermal equilibrium, the temperature will also be TL. Now, you see from the surface tension we know that PV minus PL for a spherical drop is 2 sigma divided by r, where r is the radius of the size of the bubble. So, r is the size of the bubble, and this sigma is the interfacial tension, PV is the pressure internal to that bubble, PL is the pressure of the liquid, right. Now, you see that from Clausius-Clapeyron equation, we will discuss it in thermodynamics. We have d ln p sat dt is equal to this delta H divided by RT square. Now, we will integrate this from two states, once from one state to another state. Then in the first state, you see the liquid is saturated, its pressure is PL, still PL, and its temperature is T sat. We are going to superheat it, where pressure is PV, right, in the bubble. In the bubble, the pressure is PV and the temperature is TL. So, if you integrate, I will get ln of PV by PL is equal to delta H divided by R, and then dt by T square, its integral will be minus of 1 by T. So, 1 by TL minus 1 by T sat to 1 by TL. So, What will happen from here? So you see, this we can write as ln of 1 plus PV minus PL divided by PL, and if this difference is not pretty high, we can approximate it as log of 1 plus x is equal to x, with that is PV minus PL divided by PL, and that's equal to delta H divided by R. Denominator we have T sat into TL, and in the numerator it will be TL minus T sat. So that is the degree of superheat. Right? So this is typically the degree of superheat, and we have PV minus PL divided by PL, and now we will use this, gives the equation to replace this PV minus PL, which is 2 sigma divided by R. So it is 2 sigma divided by R is equal to delta H into PL divided by R, capital R, into T sat TL into delta T. So that is the degree of superheat. So delta T is proportional to 1 by R. What does it mean? As you go on increasing the superheat, right, your radius of the stable bubble will decrease. Okay? That means the system can sustain smaller and still smaller size bubble, and that depends on the degree of superheat. Just like as an example, if I have TL 110 degree, T sat which is 100 degree, right, PL definitely its atmospheric pressure 013 bar, right, and everything else are constant. So if you calculate, I will get R is equal to 3.55 into 10 to the power minus 6 meter. What does it mean? It means that bubbles with size greater than 3.55 into 10 to the power minus 6 will be stable. So it means that bubbles with size greater than 3.66 micron are stable. If I have a bubble of 10 to the power minus 6 meter only, that is 1 micron, that this may collapse. Okay, and actually this will collapse. However, in real life, real situation of this is a calculation based on homogeneous boiling. In real situation, where we have, you see, the size of the bubble is lower, even it is 1 micron, we will see that it will sustain in that system. The reason basically it's heterogeneous boiling we are dealing with, and this is much more favored, right? This heterogeneous nucleation, actually this curvature induced boiling of this local scratch or pit holes, they actually favors this boiling even at much lower excess temperature, where a bubble size which is much lower than this will still sustain. So that's all about this boiling process. The flow boiling phenomena, you see that flow boiling phenomena where in a hot pipe we have a delivery of the subcooled liquid, and maybe we have the different regimes, like initially there will be a subcooled boiling, then there will be a bubbly flow, then the slug flow, then annular flow, then mist flow, everything, the details of it definitely in a qualitative fashion we will discuss when we go for this process equipment, discussion of the process equipment, that is the evaporators, right. So that's all about the pool boiling. So in the next session we are going to discuss about condensation. Thank you.